Hi everyone, welcome to Silo. Thanks for making it by the NeurIPS finals week. So thank you for coming here. It is an absolute pleasure to have Justin here today. He is a tenured associate professor in MIT, and he is here to tell us a lot about his recent work. From what I heard in the morning, it's going to be a lot of interesting insights about generative models like diffusion and beyond. So looking forward to hearing what Justin has to say. Justin, of course, apart from being faculty in MIT, has won a lot of prizes with very diverse work, all the way from ACM SIGGRAPH test of time, which for those of you that know, SIGGRAPH is not a piece of cake, let alone the test of time award, to a lot of very cool work on numerical methods, and I think even a book on that side. So he has done very, very cool work. So looking forward to hearing more about the insights. Thank you for coming, Justin. Looking forward to your insights.
Well, thank you so much for the introduction. It's such a pleasure to be here. What a nice spot to be hanging out. And I've had a very cheese-intensive morning, so I feel like I'm experiencing Wisconsin and hopefully can make it to the end of this talk. But in any event, it's such a pleasure to be here today. I tried to tailor a little bit to this audience, and we'll see if I was successful or not. But mostly just share some research from our team at MIT, specifically aligned a bit to this generative modeling space with somewhat of a geometry flavor. So I'm around all day today. It's my pleasure to chat, grab coffee with just about anybody while I'm here. For those of you who I've not had the pleasure of meeting yet, okay. There's like Zoom layered on top of other stuff, and switching slides appears to be a challenge, but we'll make it work. In case I haven't had the pleasure to meet you, I'm Justin. I come from MIT. I lead a research group with a purposefully ambiguous name that we study geometric data processing, and I'll say a little bit more about that in a second. MIT is, I think, one of the most wildly bureaucratic and confusing academic institutions. Because of that, we're attached to all kinds of different efforts within the university, but essentially, this is a research team in applied geometry that studies problems in all kinds of different spaces, from statistics to computer graphics and numerics. So specifically, our team has kind of a funny, like Bert and Ernie kind of situation between two different areas of geometry that I think are often considered very different kind of distinct parts of computer science, but largely part of, as a byproduct of my own weird PhD, which sort of started in one and ended up in the other, we have some research in both. So on the one hand, our team works a lot on problems of processing geometric data. So for instance, my own personal background before starting a PhD was working in an animation studio. And indeed, we have a lot of friends in computer graphics world, where really the algorithms that you're trying to work with are what I think we would conventionally think of as applications of geometry and computer science. Things like physical simulation, autonomous driving was one of the big ones that we worked on the last maybe 10 years or so, where, for example, the kinds of problems that we're thinking about involve like, how do you design a machine learning model that ingests a piece of geometry and makes an inference about it? Or how do you design algorithms for simulation, 3D modeling, and so on? But then the other half of our research team works on kind of geometric approaches to processing data, where now your data is maybe embedded in some high-dimensional domain. And essentially, our sort of ongoing thesis is that these two areas are very strongly supportive of one another. I have a lot of students that cross the divide from one side to the other and back, and are able to think about using these nice low-dimensional problems that are very tangible to inform the reasoning about kind of abstract high-dimensional machine learning problems and vice versa. So for example, my own PhD was in an area of maybe statistics optimization known as optimal transport, which at the time we thought was going to be a really cool tool for keyframe computer animation. And in retrospect, that was a really bad idea, because the whole point of optimal transport is to be as uninteresting as possible, which of course is not what computer animators want. But it did end up being a very useful statistical tool in some inference settings. And so sort of the structure of our research team is sort of follows that weird history from my own work. So today we'll be largely in the second category, hopefully that's aligned with the seminar. Of course, at any point, if you want to derail me, it's very easy to do that. And I'm more than happy to tell you about all the fun problems that we're studying in computer graphics domain as well, largely with the PDE and optimization. Before I get started, I should tell you, of course, that I am just a conduit for all the cool stuff that my students are doing. Really, if you have hard questions, these are the people you should ask. I'm here to just take the credit and do what professors do, I guess. But really, these are I'm so fortunate to work with this team of really brilliant folks at MIT, and really my job is to just stay out of the way. In particular, I wanted to highlight that most of the work I'll tell you about today, I've tried to be careful with attribution and all that, is from my student Chris, who's just about to graduate and is starting a faculty position at Rutgers. So if you like this kind of stuff and you happen to be an undergraduate or a master's student here, I would strongly suggest applying to Chris's research team because it's just getting off the ground and he's really awesome. Okay, so in any event, we'll dive into some technical stuff with a little bit of high-level motivation, and then time permitting, I'll try to tell you about 3 different projects we've had in our team, roughly at this kind of intersection of geometry and machine learning. I guess that's kind of a reasonable high-level starting point. Here's kind of a funny thing that I think it took me a long time to realize. I mean, our research team is certainly in the fringes of the machine learning space. I don't think we can claim to be sort of central researchers in this domain, but certainly we interact with these tools daily. And one of the things that I found so overwhelming when you look into the machine learning literature is you look up all these different methodologies and architectures and so on for learning. And here I just went onto Google Images and looked for a diagram of machine learning architecture, and you see these wild pictures with circles and arrows and human brains and weird robots and cats. But the reality is that I think for a lot of the analysis and statistical problems that we study, even going back to just the multi-layer perceptron, we can abstract away a lot of these different kind of architectural details and think of a machine learning architecture in this vastly oversimplified fashion as this big sequence of matrix multiplies and nonlinearities that take you from this sort of raw data format that's going into your learning model all the way to some decision. And there's all of this mythology and understanding that has to go with what that sequence of transformations looks like, right? And especially these days in this world of large models where there's these matrices of millions or billions of elements and there's so much going on, I think it's a pretty reasonable kind of analogy to think through sort of how these different layers of your machine learning architectures are you taking the geometry of your raw data set and then slowly and progressively reshaping it into some format where you can do inference or whatever your task is in a more abstract fashion. So from that perspective, of course, your learnable parameters here are maybe elements of the matrices, and you get this sequence of embeddings as the outputs of your layers. Now, obviously, those of you who are machine learning engineers will be very quick to correct me and tell me all of the different reasons why this is a really bad abstraction, and I totally agree with you. But I do think from just a high-level perspective, that'll be good enough for us today. And indeed, this perspective has been around a long time. So for example, here's sort of a famous early experiment that people did in convolutional neural networks, where sort of one thing that you can figure out is that with many of the state-of-the-art trained CNNs, if you look at the sequence of embeddings, what they're essentially doing is learning some version of abstraction of your data that goes from basically some wavelet-looking feature all the way to high levels that's trying, in this case, to represent a face. Incidentally, I'll take these 18 seconds to argue that I find these diagrams to be completely worthless and just the world's most complicated way to illustrate literally a matrix multiply, right? That's all these these pictures are, and I wish I knew that when I was an undergrad. In any event, so because of this sort of very abstract picture, I think there's a lot of really interesting possibilities and for research that I think in some sense sidestep one of the big concerns that we have today in modern machine learning work, which is that a small lab full of math dorks like my own just doesn't have the resources that we need to be able to train some giant model. That we just don't have the compute, we don't have the expertise in order to, for example, make our own, whatever the latest buzzword is, foundation model for processing data. But what we can do is take all of these different models that exist out there in the world and try to take a pair of tweezers and understand how they behave, how they transform our data, a little bit from a phenomenological perspective and also from a medical one, and then try to leverage that and reshape it in different ways that are useful for other tasks. And so, for example, this gives us many different embeddings of our data sets. They give it different geometries. For instance, I put in quotation marks here because I'm a geometry person. That people talk a lot about there being some manifold underlying your data set. One might ask whether that's really true or not, but it's certainly a reasonable analogy. We can talk about how to adjust the geometry of these embeddings to make them better for different tasks, or even how to maybe regularize some small-scale model to have some behavior that imitates the larger pictures. So this is obviously a very abstract and high-level story. I mean, really, my goal here is a very loose way to glue together 3 research projects that I thought were fun, and I'd share with this audience here. I guess this is my luxury post-tenure is to be able to just say that. But essentially, I think all of these can be understood as different techniques for understanding the shapes of embeddings that kind of come out of different layers of learned models and manipulating and navigating those embeddings in different fashion. So in particular, I'll start by telling you about some of our work in the diffusion model space. Diffusion models these days are some of the trendier models for generative AI style problems. Specifically, I think in image generation is the main application where we see these things getting used. But these days, also you see them in robotics, you see them in audio, all kinds of different domains with varying levels of success. And I think one of the questions you might ask is kind of like, what are the statistics of those domains that make these diffusion models work so well in these different settings? I'll tell you a bit about that. Then I'm going to switch modes a little bit and tell you about some of the space that we have in fine-tuning and adjusting learned embeddings. So this first one is all about just navigating. Like once you've learned a useful embedding of your data, now you want to start generating new data points that kind of are distributed like the old one. A different thing you might want to do is take your favorite language model or statistical model and adjust it to be good at some particular task, or maybe to have knowledge of a data set that I cannot use to train my full large model. And we'll talk about some interesting work that we've had in that domain as well. And then finally, in this third thing, actually, I probably should have swapped 2 and 3 because 1 and 3 are linked to each other. I'll tell you about some work that we have involving trying to design smaller models whose intermediate layers have some structure in common with these large learned foundation models that aren't regularized explicitly. So that's our plan for today. And if at any point you're bored, you've had enough, just let me know and we'll call it. So with that, let's get started. And in particular, I'll tell you about some of our work in diffusion modeling. Again, I should be careful to note this is largely work that's been led by my student, Chris, where really this is the byproduct of his vision in this domain. And I think really stands out as a bit of an interesting combination of perspective, not just from statistics, but also in some sense from just computer engineering and even numerical methods, which was good for a person like me that has more background in those spaces than in that. So we'll start out with the sort of basic setup in case you're not familiar. So in general, in this kind of generative learning space, we have this somewhat ill-defined task, right? We're given a big data set of data points. So think about like a big collection of photographs that I've collected from the internet, like every cat on Google. Now, each of those data points is some xi. And our typical mental model is that those points are drawn from some underlying distribution, right? So for example, people talk about maybe the distribution of natural images on the internet. And obviously we do not have access to that distribution, but we do have samples. Right? In other words, we have individual photographs, but we don't have like the density function of that object. In fact, it's not even obvious that a density function exists. And then our task is to now draw novel samples. And I want to pause here because I think this is typically how people motivate this kind of generative machine learning task. And I want to note that this is a totally ill-defined thing, right? Like it's really not obvious. Like in some sense, what does novel mean? And of course, without having some prior understanding of our distribution of row 1, this task really makes no sense at all. And so it's one of the kind of miracles of modern generative machine learning is how far we've gotten without even kind of writing an explicit prior on these things. And oftentimes we're really relying on our architecture, our training procedure, and so on to provide some species of regularization that a posteriori we try to explain, which is very different than, for example, the world that I grew up in where like you carefully design maybe a Bayesian prior or something like that. You analyze the bejesus out of it and then you try it. So we're in this new kind of universe where kind of experiment first and write equations later. And so our team is going to try and bridge that gap just a little bit. So in particular, within this domain, there's a class of models that are particularly popular. This includes diffusion models, flow matching. I'm sorry, Zoom is like has 12 different reminders on my screen at once. Okay, which do the following thing. And I think really in some sense is reflective of a high-level breakthrough in this kind of generative or sample-based approach to machine learning, which is rather than just in one shot trying to learn how to generate samples from a distribution, you instead kind of learn in a progressive fashion, right? This is true both for images and for text, right? So for example, these autoregressive text models are somehow doing something similar. But in diffusion models, essentially what you do is you define some stochastic process where you start with a distribution you know how to sample from, like a Gaussian. And then you write down maybe a differential equation, either ordinary or stochastic, that takes you from that guy to the actual distribution you want, like this checkerboard here. And the learnable parameters are maybe the dynamics of that process, right? And so in particular, your algorithm looks like, if I want to draw something from our unknown distribution of row 1, I draw something from row naught, which is usually just some boring Gaussian thing. And then I just solve like an ordinary differential equation that flows through some velocity field, and that becomes our variable, right? Or there's like a slight variation of this thing where you basically do some version of forward Euler integration and add a small Gaussian, and then you get to use fancy SDE language instead. But that's really all that's going on behind the scenes. And there's all kinds of different ways that one can go about this. I mean, one thing that you might know from either fluid dynamics or undergrad ODE or whatever is that this velocity field is not unique. There are many different ways to take a Gaussian and map it onto the same distribution here. So there's actually a bit of a design decision, and in some sense, that's where engineering happens, right? That some of these are probably easier to learn than others. Okay, so specifically, a class of algorithms that seems to be very effective includes diffusion models and flow matching. These are basically the same up to some rescaling of variables, which learn the velocity field in a really interesting and straightforward fashion. Essentially, so remember that V here is the velocity field of our dynamics. This is like the thing that's moving samples from a Gaussian to your final distribution. And in particular, you set up this simple variational problem, which does the following thing. It draws, I'm sorry for some math notation here. I can't help it. It's a professional hazard. I randomly draw a data point X from my data set. That's row 1. I randomly draw an epsilon, which is just normally distributed. Notice that basically I can draw both of these things. What I don't have is the density for row 1, right? But I can go up on the internet and download a cat. That's easy enough. And now I have this particular loss function, which essentially is trying to do the following thing, where the velocity field is kind of looking like the difference between the Gaussian random sample and the sample from your data set. And one thing that you can prove is that if you optimize this thing with respect to functions V, not neural networks yet, just functions V, then the velocity field V here truly does take samples that start at a Gaussian and transform them to your final distribution. This is called flow matching, right? Okay. By the way, that's not entirely obvious. You have to actually justify this thing. I think the easiest proof kind of comes from a nice application of Bayes' rule. But it's kind of, this is a very straightforward procedure and one that looks a lot like how people train diffusion models today, which is very simple. You randomly draw data points, you randomly draw Gaussians, you interpolate, then you try to get your neural network to predict that. Okay. So this is a very elegant and simple training procedure. And indeed it is roughly what people do in practice. And initially what was proposed, including in this iClear paper and some earlier ones as well, is that you parameterize V as this unknown neural network. This thing becomes your loss function where you just randomly generate or draw these things, and then you can do stochastic gradient descent. Hopefully that story makes some sense. Okay. But here's kind of an interesting thing. Let's think about this as an optimization problem, not for a neural network, but for a function V. Right, so before I begin inserting all the complexities of like neurons and activations and so on, maybe I'm a mathematician and I want to say like, what is the optimal solution to this problem in an ideal universe where I can just find any function V I want? I'm not restricting to the set of things that my neural network knows how to learn. Hopefully you guys understand the distinction there. And I think, people often throw around like these universal approximation theorems as some bridge between these two, right? That like, if I make a really big neural network, then essentially I can approximate any V. So I think that's a reasonable question. And here's the thing that I think is kind of interesting about flow matching and other problems in this domain. As a function of neural network parameters, this is a very complex loss function because of course it is. There's ReLUs and matrices and all kinds of stuff. But as a function of V, this is least squares, right? And here's the thing you might remember from undergrad linear algebra class. Least squares problems have solutions that you can just write down. There's just, a closed form formula. And in fact, that actually is true for diffusion models. So there's this kind of interesting, I would argue, slightly neglected fact, which is that if you truly believe the story on this slide, and you truly believe that our goal in life is to make our neural networks as large as possible, then in some sense, we know what these are going to approach, and we don't need a neural network at all. We can just write down a formula for V. I decided to write the square function, which turns out is linear related to V. I don't know why I did that, but essentially the formula for V looks very similar to what I wrote on the slide. And it's really boring. It's just a linear combination of your data points. And that kind of makes sense, because let's think back to our original story. Remember our goal here, I have a bunch of points sampled from a data set, and now I'm trying to make a sampler that kind of imitates that. What's probably the best sampler in the universe? Well, it's the one that randomly draws an index in your data set and gives you back that image. And in fact, that is the global optimizer of this objective function here. If you look at the globally optimal V, is the world's most complicated way to sample from your data set. And so my student Chris asked a totally reasonable question, which actually I think it was a little bit surprising to us, was not studied in this domain, which is you have a closed form solution for the diffusion model problem as you've written it down. You have the thing that comes out of neural networks, and the sort of like numerical analysis brain of mine would say, well, okay, well then we should compare these two and do error analysis and try to understand, like, is the training procedure that people use for these generative models at all resembling the solution to these problems? And of course, the answer is no, because if it were, well, then you would have a bad sampler, right? In some sense, the whole reason that these diffusion models are performing well is because they do poorly at the task at hand, right? And so I wanted to pause here because I think this is a really interesting kind of philosophical question. In fact, there's a few that are all tangled together here. One is like, why do we use neural networks for this problem? If we have a solution to it, it's just a kernel, right? This is a Gaussian kernel at the end of the day. It's called diffusion models, but it's not surprising that this, you know, at least for small data sets, it's not obvious that I need to train anything at all. And so there's a lot of hypotheses you might guess for like why we might want to use a neural network for this. One is that it's compression, right? So in particular, if you look back at this formula that I wrote down here, there's a giant sum over your whole data set, and maybe that's intractable. So I'm using my neural network to just kind of remember my data. Now that's a sensible hypothesis. We can just, at least for small enough data sets, compare those two and see if it's compressing. The answer is no. So we don't think that that's likely. But the second is probably that, well, at least we get the right vibes out of these models. You know, they generate interesting samples. They feel novel. You know, as we know, neural network training, due to some combination of probably stopping before optimality and the architecture itself, leads to some bias where the samples that you get are not just in the data set, but other stuff that are kind of nearby and distributed similarly, right? And so most likely that second one is kind of the explanation for why in practice we use a neural network for this problem, which of course begs the question, which by the way, I'm not going to answer. I'm asking this as if like the next slide is going to give you an answer, and sadly that's not the case. What does it even mean to generalize for these kinds of tasks? Because in particular, I think we're all stuck, you know, at least for me, I teach our undergrad machine learning course, and we teach this beautiful story about generalization for supervised machine learning, right? That you have a data set, you withhold part of your data set, you train on this one, you test, you have these nice generalization bounds that kind of say, well, you know, as long as my model is like expressive, but not too expressive, then maybe I can make good predictions on data I haven't seen yet. The phrase data I haven't seen yet actually really doesn't make sense for generative modeling. There is no notion. And so a lot of, I think what you really see in this domain is just qualitative in nature, right? You look at the images that are in these models, and you say like, yeah, do they look kind of novel, but not too novel? And that's as good as we can do. Right? And so it's kind of an interesting space, but there's a lot of math. I mean, when you read these papers, there's like stochastic differential equations and all kinds of crazy bounds getting thrown around. But the actual thing that we're after is quite tricky. And I pose that largely as a question because I think it's one that's worth thinking about. Like, how do we make this systematic and thoughtful? I think it is really an open thing. So in any event, one question you can ask just from a modeling perspective is you could say, well, okay, so my neural network for learning a score function or this velocity field V is not imitating the global optimal solution. So one thing I can do is kind of work around the edges in both directions. I could take the learning procedure and edit it, or I could take my closed form formula and like propose small changes and see if I could introduce some kind of bias to the closed form model that maybe imitates the reality of neural network training a little bit better. And indeed, for fun, we played with a few very simple things. So one of the hypotheses here is that neural networks have a bias toward learning overly smooth functions, right? This is a well-known thing. And so one thing you might do is just try to kind of smooth out the learned velocity field that comes from this procedure. You have to be a little bit careful how to do your smoothing, it turns out, because some kind of doesn't make sense for this particular sampling problem. But what we found is by basically convolving the right kernel against Gaussian inside of that formula, at least for very simple sampling tasks, we can overcome a bit of this just sampling from your data set aspect and actually imitate, at least on small data sets, the same kind of bias that you see in learned diffusion models at the larger scale. Now, what I don't want to claim is that we have a state-of-the-art diffusion model with a formula with, just inserted Gaussian in the right place. That's awfully optimistic. But what we can do is begin to model the sort of things that get learned in this procedure. And I think really we have more questions than answers here. That essentially, I think there's a world where you say, okay, for all we know, 95% of the time, the training time for a diffusion model, which is usually quite large, is spent just regressing a Gaussian. And then that other 5% is spent learning an interesting embedding of my data set, right? Then that would be a good thing to know, because then maybe I can make a really efficient diffusion model that bypasses all that boring stuff and just learns the interesting part. And sort of our initial experiments in this domain seem to suggest some possibility that that could be the case. So for example, maybe I'll skip over. We have a very simple smoothed out formula that after a lot of tuning of exactly the right kind of smoothing, we can get to, at least on very simple examples, for example, this goofy checkerboard data set, which everybody uses as kind of just a sanity check, begins to kind of have the right bias for these sampling tasks. And then we were able to get a sampler for images, not on the largest data set, but at least on this kind of celeb A, faces kind of data set, a relatively good sampler by combining basically two things. One is smoothing out the closed form formula, and the other is really working very hard to learn a good embedding space for your data set. And so I think this is an interesting kind of question to ask, which is we put a lot of statistical effort into learning a good embedding of our data into some space where it probably forms a much simpler shape than where you started. And I'll tell you more about that in project number 3. I'm realizing my talk is organized in a poor fashion, and for that I apologize. But after we do that, we can do sampling in that latent space using this very simple closed form procedure, no machine learning involved, and actually get pretty convincing output for our sampler. Now, this is clearly not on par with what you're seeing from Google or OpenAI, but I do think it's a really interesting kind of little motivator for asking these questions of like, exactly what are these models learning, and can we distill our training procedure to just learn that one part and maybe bypass learning all the other stuff, which is just mathematical formula or like the world's most complicated Gaussian? And I think we just don't know. And there's some really interesting scientific questions here. I should share we have a few follow-ups for this paper. Sadly, I'm already over time, so I won't share too many details today. But my student Artem looked specifically at the image model case and found in that particular domain a really surprising result, which is that these trained models actually resemble just a linear diffusion model extremely well for like 95% of the sampling procedure. So in other words, like this velocity field V, specifically, if you assume that your data set is Gaussian, then it becomes this thing called a Wiener filter, which is classically known in image processing. And you can replace many of the diffusion steps with that thing and not affect the quality a whole lot, which is like another clue that maybe there's some simpler structure going on there. And as a byproduct of his work, he sort of, I don't want to say disproved, but gave some evidence against an earlier hypothesis, which is that maybe the reason that these diffusion models generalize has to do with the machine learning architecture. So for example, for images, maybe you're using a convolutional neural network where there's some translational invariance, which isn't in that original problem that I wrote down. But what he showed is that the same phenomena emerge even when you don't use architectures like that, that it has more to do with the statistics of your data probably than about the architectural decision. And then most recently, my student Chris again did a really clever calculation, which I like. This is related to influence functions and statistics. I know some people here work in that particular domain, which is if you're looking to do all kinds of fun mathematical analysis of diffusion models, the fact that it has a closed form solution makes doing your math a heck of a lot easier because there's just a formula. You can do high school calculus on that instead of having to like prove complicated byproducts of like theorems about differential equations. And so one of the things that you can do is just differentiate that formula specifically in the shape of your data set. So in some corners of statistics, this is called computing a influence function, at least if it's on the weights of your data set. And what that gives you is a really interesting thing, which is a sensitivity analysis. So one question that you might ask is, let's say that I introduced or removed points from my data set. How does the output of my generative model change? So for example, maybe I want to know, like, oh no, like this thing is creating copyrighted content. What part of my data set is causing that? Remove it. Then you might want to ask questions like this. Or like, I think another one that is neglected and is worth studying a lot is attribution, right? A lot of the data sets, especially for creating images, are curated from artists created content. And one of the big ethical discussions that we should be having right now is whether it makes sense to generate new images and not credit those artists or give them compensation. But the first step in that direction would be simply to figure out like what pastiche is being created by this generative model, which is currently unknown, right? But like when we evaluate these black boxes, it's really hard to go back and attribute a given generation or utterance from this model to a particular data point. One way to do that would be to solve a sensitivity analysis question, like how much would my output have changed were I to have removed this piece from my data set? In any event, because we have these nice closed form formulas, what happens in this research paper, which is currently on arXiv, is you can work out the sensitivity analysis in closed form. You can work out this derivative pretty cleanly. And the kind of nice thing is you can write it as a recurrence. You can write it in terms of the diffusion model itself. So Chris did a really sneaky thing, which is, okay, you use your closed form formula to derive your sensitivity analysis, but you actually can write it in terms of just evaluating the model multiple times, which allows you to do it on trained models, assuming there's a bit of a leap of faith that the same sensitivity kind of formula should still work, even if your learned model is kind of inexact. And so this actually gives a procedure for analyzing not just models that are done in this very kind of straightforward closed form fashion, but also the learned ones as well. And we show empirically that that's actually a pretty reasonable engineering decision. So more to come soon. And then finally, my student Artem in this space also has looked at specifically algorithms for 3D generation. And in that particular case, this one's a little bit different, so I'm happy to tell you about it over coffee. He spent 2 years digging into every single equation in the generative model, specifically for 3D content, where there's this added complication of typically using 2D image generators to create 3D shapes because there just isn't 3D data out there. And kind of answered this question of like, well, the 3D geometry that comes out of those models is way worse than the quality of the 2D images, which maybe feels reasonable because 3D generation is just a hard problem. But then he did kind of an interesting thing, which is he replaced the 3D representation behind the scenes with just a 2D pixel grid. So in other words, made the world's most complicated image generator where you have this procedure for generating content that is used to inform procedure for generating other content, like you have a 2D image generator used to inform making 3D content. You can actually use the same algorithm to use a 2D image generator to inform another process for making another 2D image just as a benchmark, and found that all the same artifacts actually persisted in that case. So in other words, it wasn't the fact that you're learning 3D stuff that was the problem, it was the learning procedure itself. And then was able to explain the difference, fix the formulas a little bit, and then also improve the 3D case as well. So anyway, if you like really fine-grained kind of differential equation analysis, I encourage you to take a look. It's a fun paper. Okay, so in any event, I think hopefully you understand the high-level point, which is that essentially, when it comes to engineering these like generative models like in diffusion, there's a very complicated story. And this, by the way, is not unique to our research team. There are other ones in this domain, for example, some folks at Flatiron Institute that have come to a very similar conclusion. So there's some interaction between the geometry of your embedding, that like reshaping your embedding into some nice shape makes the sampling procedure easier, which is not surprising. The training procedure itself, noise, and so on, that are all creating these things to work well, even if we don't have a nice underlying theory that could explain generalization at the most broad level. And really, this is just a call for help. You know, we need all of you guys to come up with the interesting sort of theories that explain what's going on. And I think it's not just a question of theoretical research that us academics can kind of do as a fun byproduct while OpenAI does the real work. I think there's some real promise here for engineering lightweight models that have similar performance to these giant things, once we can explain where machine learning is actually necessary in this pipeline. And I don't think we have a good answer for that. In any event, because I've organized this talk poorly, I'm now going to jump to a completely different topic and tell you a bit about not just navigating these learned embeddings, but also editing them in different fashion. This is work largely from my former postdoc Jiaqing, who moved to Meta, as well as my student Rickard Gabrielson, who's about to graduate. And this has to do with taking those matrices in these large models and learning to fine-tune and adjust them for different tasks. And this is something that we see in industry all the time. I have some generic pre-trained maybe language model, and maybe I have some in-house data sets. So for example, maybe you're a lawyer and you have a bunch of documents that you can't release. And now I want my model to be an expert on that stuff. So I do just a little bit of additional training to incorporate that data. And one of the issues there is that those data sets tend to be a lot smaller than the original model. So maybe it doesn't make sense to train all of the millions or billions of weights in the original guide. Or maybe you're an academic, you don't have a million GPUs to train on, and you just need some lightweight training procedure. And so in practice, there's one procedure that seems to have arisen as a very popular technique, which was very much just kind of built on some engineering practice. Here I've borrowed a figure from the literature. I think this is so much fun. Somehow, I guess this particular corner of machine learning is more comfortable with like a pictorial, I don't know, version of a matrix multiply. But in any event, there's this procedure called low-rank adaptation for fine-tuning neural networks, which is a very straightforward thing, which says your neural network are these giant matrices, which I'm going to call W naught, which are mapping your data into these other spaces, followed by some nonlinearity like ReLU. And typically when you fine-tune, maybe you adjust these W naughts, but for whatever reason, it's too big. Your data set's too large, or your GPU isn't good enough. Then one thing people will do in practice is rather than updating every element of W naught, they will make an additive change of a low-rank matrix and instead try to optimize for these two matrices B and A, which are like skinny and tall. Right? This is a way to reduce the number of parameters that you have to learn during the fine-tuning procedure. This is part of a larger literature called parameter efficient fine-tuning, but I think it's actually a pretty sensible one. Like, I don't know, as a person that's much more comfortable with numerical linear algebra than with machine learning, like if you look at this as kind of like a reasonable thing, it kind of resembles what we used to do, for example, for the Netflix problem back in the day in matrix completion and so on. So low-rank adaptation has been around for a while now, and I think in industry is one of the more popular ways that we have for fine-tuning. And our postdoc Jiaqing did kind of an interesting thing, which is he dug through the user manuals for this software. We were working with friends at IBM at the time, and we were just trying to get a handle on like what people do in this particular domain. And one thing that he noticed by some, I don't know, miracle or his own brilliance, I'm sure, was that they all offer the same weird practical advice. So again, what you're going to do is you go fix these giant matrices W naught in your neural network, and you're just going to fine tune this product B and A. So you now have two different matrices that get updated. And all of them follow the same general procedure, which is typically when you initialize these fine-tunings, you want the product of A and B to be 0 because you want to start out at your original model and then learn to perturb it. And so they all say the same thing, which is initialize B to be 0 and A to be random and Gaussian. Right? Or there's some other pieces of practical advice which are kind of similar, where like maybe the learning rate for one of these two matrices is larger than the other, which are things that maybe you wouldn't have guessed just looking at this low-rank adaptation problem at its face. So Jiaqing did the completely sensible thing as just like a scientist, which is he said, well, that seems odd. Why don't I do the opposite of that? Like, why don't I zero out A and have a Gaussian random B? And what he found is the performance degraded significantly. And this was really surprising. I mean, so it's like essentially we were all reading these user manuals thinking like, what an odd choice. But it turns out that this is actually a really critical little piece of the puzzle to make these low-rank adaptations work, which really caught us by surprise. So then we started stripping away more and more pieces of our neural network, using simpler and simpler models and testing out this fine-tuning procedure, and found that this is very much a pattern that gets repeated. And in fact, if you remove all of your nonlinearities whatsoever, still this practical advice turns out to be the right thing for learning low-rank changes to matrices. And finally, we were in the domain of least squares because we've removed all the nonlinearities, so you can actually prove a theorem. And here's the kind of surprising result. Roughly, what you can prove is that you can lower bound the performance of fine-tuning only one of these matrices, making the other Gaussian random in terms of the other, right? And the reason you can do this kind of similarly to what I mentioned for a diffusion model is like there's a closed form formula for A and B where you fix one and optimize for the other, because this is just least squares. And so you really can just work out the statistics of this thing. So at least for linear models, you can justify this procedure. Like really, fine-tuning one of these matrices is more important than the others. For certain corners of statistics, this is kind of an unsurprising result in retrospect. I think the way that you can view it is there's a lot of results in random matrix theory that say if I have a high-dimensional data set and I just randomly project it onto a low-dimensional space, a lot of times structure is preserved. And so in some sense, if I just make this A matrix here, by the way, I think my slides keep swapping A and B, and for that I apologize. If A is just Gaussian random, it's kind of serving the role of that random projection, which often preserves a lot of structure, whereas B is really critical to the learning process. And so somehow that's what's getting reflected here, just in this new weird nonlinear high-dimensional universe that we're in machine learning. And so in fact, what Jiaqing did, which is kind of fun, is he said, well, in that case, we can probably get similar performance with half the parameters by doing the following, which is fixing A to be Gaussian random and not fine-tuning it at all. And if I do that, then I don't even need to store A. I can just store the random number seed that I used to generate it. So this is very efficient in terms of parameters. And in fact, here's a useless table. If you're able to read it from a distance, then your vision is better than mine. But the main takeaway is that, in fact, you can get very similar performance to fine-tuning both of these matrices if you design your procedure really carefully. In fact, you can get better performance because you can now have 2 times the number of parameters in the matrix that matters. And so this was a nice kind of practical takeaway that was built on this little theoretical observation. Now, then we got a little bit greedy. So I think one thing that you can learn from this research project is this parameter efficient fine-tuning procedure, right? This learning a low rank update is itself not that parameter efficient. Oh, yes.
What did you say about A? So you didn't
sorry.
store it? I mean, it's completely random.
That's right.
Replace it with some like a Fourier transform? Or...
But that's a good question. So Fourier transform doesn't turn, it turns out you can't, it needs to be random.
They really take a Fourier transform and truncate it. That's not
maybe for images specifically, but for generic stuff like language, we were unable to do that. So our theory here is for Gaussian random A. I believe Rademacher would also work, but I'd have to double check.
Okay, but do you still have to store that? Or you
no, yeah. So what I mean,
generate on the fly.
You know, assuming you're okay with pseudo-random number generation, you generate it on the fly and you remember your seed.
Yeah,
that's right. It was a really sneaky trick. That's right. So an interesting takeaway of this work is that like this parameter efficient fine-tuning is certainly more parameter efficient than fine-tuning W naught, but apparently it's not entirely parameter efficient in that we were able to remove half and still do pretty well. So then my student Rickard asked the question of like, well, wait a second, maybe what's getting learned in these low rank updates is even lower rank than we think. It's just a question of parameterizing it the right way. So as kind of a stepping stone to that, immediately while we were doing this work, this big ecosystem of low rank updates has kind of appeared on the internet. Initially, he actually made his own data set where he took one of the large language models, I forget which one, then fine-tuned it on like, I think 5,000 different data sets. So we have a data set of A-B pairs that are like, you know, I have my language model, now I have my language model that talks like Shakespeare, and I have my language model that's like good at repairing VCRs and, you know, whatever, like all these different updates to this thing. And so now you can do kind of an interesting meta-level statistical analysis and say, what are the statistics of the A-B pairs? And what do they tell me about the sort of manifold of ways that I can take a fixed large model and update it in an interesting fashion, right? Because like if I took the weights of a large language model and I just randomly perturb them, chances are it won't be meaningful. And so there's a question, which is what is the dimensionality of that space? Like clearly it's less than the number of elements in A-B. We showed that in our previous project, but how big is it? I think we still don't know. And so in this next project, what we proposed was kind of an interesting compression question, which is as follows. You can imagine a world where everybody has their own little personalized low rank update. You know, like, for example, I like my language model to talk to me as a professor and give me suitable amount of respect. And maybe other people want it to talk to them as a friend or whatever. And so everybody has their own little A-B pair that they want to have kind of served up with them as they put in requests to the language model sitting on a server. And in that case, there's kind of an interesting question. So typically for one of these low rank updates, it's roughly 1% of the parameters of the size of the LLM. But if I want to make, you know, low rank updates as a service, then I have to serve up thousands of these things. And then now the A's and B's are actually the things that are taking up all my memory on the computer. It's not actually the foundation model. And so squeezing out all of the information you can out of a collection of these is kind of an interesting thing. And so that was the question we asked next, was how can we make a sort of client-server system that swaps these things in and out really quickly? And in particular, how could you compress a set of personalized updates for one of these models? And we did so with a pretty naive approach, really. So essentially, we worked out some analogy of principal component analysis for this collection of A/B pairs. You have to be a little bit careful how you do PCA in this universe, because what matters is the product of A and B. So you don't want to just do PCA on the A's and on the B's. You need to like do some fourth order thing. The good news is this looks like old school optimization. So like I know how to do this kind of stuff. But essentially, by doing that, we were able to compress these things. This is sometimes called joint diagonalization, like big collection of matrices. You're trying to get some kind of common eigenstructure. And essentially what we ended up doing is making a compression that kind of looks like the following. So we have one big shared basis U and V, which is shared among all the AB pairs. And then you have this learnable square small matrix sigma, which is a sort of compressed version of A and B. And the procedure for doing this, I think, doesn't matter a whole lot. You guys could probably all take your college linear algebra class and come up with a reasonable way to do that. So initially, oh no, my inequalities don't make any sense. Well, if you flip the line on the left, our collaborator Christian did this sort of basic theoretical analysis one might do for a model like this. Like you basically can take bounds from principal component analysis and apply it to this particular problem. And you get a really sad bound on compression rate in terms of the elements of these A/B pairs. So thinking about them being multiplied together kind of makes this not a very good compression technique. And so initially, us being the math nerds that we are, we derived this bound and thought like, oh, okay, so this is useless. Like, in fact, like in particular, you can see it's kind of sandwiched. Like there's a 1 minus 1 over n here, and this is percent error. So that's like a thing you never want when the inequality faces the other way. But then Rickard, my student, was bold enough to just try it anyway. And he produced a plot. Here's his plot. And I looked at it and I thought, well, Rickard, okay, so that's not right. So let's try that again. And he spent another couple of days and he came back and it was the same plot again. And in particular, this is what he showed. So here, the horizontal axis is like percent error in reconstruction. So specifically of reconstructing the product of A times B. Okay, so you run one of these kind of simple PCA procedures, you project onto that basis. We're very careful to do that in the statistically correct way. And then this is just percent error. You divide by the norm of the matrix, whatever.
The percent is not fraction.
Oh, sorry. Yeah, this is fraction. You're right. Absolutely. So this is like 100%. Yes, thank you. In the vertical axis is the empirical performance on the data set on which these low rank adaptations was trained on. Right? And at the end of the day, the vertical axis is probably the one we care about. You don't really care about preserving the elements of A and B. You care that it did well on your language modeling task. Now, if you ignore the horizontal axis for a second and look at the trend in this plot, I think it makes sense, which is you do some compression, things are fine. An interesting thing happens here where it bumps up a little bit. And what's going on is that all of these different low-rank updates were trained on different data sets. There's some mutual benefit you get by like incorporating just a little bit of somebody else's data set into your low-rank update, which is what happens. This is the same as like PCA filtering out noise. And then eventually you compress aggressively and performance degrades and all that makes sense. What didn't make sense to me was the horizontal axis here, which is at that point happens at 60% error. And so essentially, I think what we've learned from this project is you can get away with criminal amounts of approximation error in these low-rank updates without affecting performance at all, which essentially suggests that this parameter-efficient fine-tuning procedure is not terribly parameter efficient. That essentially, there's very little understanding out there. Still, I mean, like this is one step, just using simple tools from linear algebra. I think there's space for a lot more work here that does something more fine-grained and kind of engineering-oriented to essentially come up with better designed ways to make these low-rank updates to these matrices in a way that makes meaningful changes to a language model as opposed to just kind of random ones. And that really, there's some real opportunity for bit engineering here. So in fact, just as a demo, Rickard took this VLLM system, which is a sort of state-of-the-art, at least at the time, kind of server for swapping in and out different language models. And of course, unsurprisingly, if you compress really aggressively and you don't have to keep swapping out these big basics matrix A and B, you just keep them fixed. You're just swapping out these little square guys, then you can serve up like, up to thousands of these low-rank adaptations with very little loss in throughput or performance, which is surprising. And I think a really practical and interesting result. So I think the kind of interesting takeaways though is that the sort of geometry of the space of interesting model updates. This is not something about the space of your data set. This is something about the space of like neural network weights. It's a different thing. is not very well understood, and it's interesting and very low dimensional in some way that we still need to figure out. And there's a lot of room for approximation error before performance drops. So some of these measures that we've had as a proxy that I think we all use kind of as reasonable loss functions in the space, like, oh, our approximation error is no good, so don't even look, actually may be a mistake. In fact, Rickard in the last year has been studying problems with recommendation systems, and there's a very similar kind of story there where the loss function for recommendation system and the thing you care about, like top K accuracy, are not well correlated. And so there's some really interesting things to be done in this space. And moreover, the kind of nice thing for me as a theoretician is that, at least in this one little corner of wildly nonlinear machine learning, your like college linear algebra skill is still relevant. But actually, the weird phenomena that people observe in this space, you also see in like least squares problems, which is heartening to me. If you like problems in this space, I'd encourage you to take a look at this fun data set that we put out there with tons and tons of these matrices. The good news is that it is a big data set, but on the scale that academics can work with. Because this is a data set of data sets, right? Like it's different fine-tuned models. And there's so many good questions one could ask here. Like, for example, is there some way to take all these different fine-tuned guys and fuse them all together into one really good model? I think we really don't know the answer to. I should also note my student On, who's more of a computer graphics guy. Again, invite me back tomorrow and I'll tell you all the fun graphics projects that we've been working on. Showed that very similar things happen in the kind of things that you see in computer vision, like these NERF kind of models, which is kind of unsurprising. And so he can apply it to like fine-tuning things that generate images and so on. One kind of fun little thing, I'll just point you to in his paper in case if you like this kind of stuff. A weird thing happened, well, not a weird thing. So my history is in computer graphics community, and the peer review procedure in that world is very different than in machine learning. Specifically, they're really nasty to each other and picky. And somebody asked a reasonable question, which is, a priori, why should I expect this low-rank adaptation thing to work at all? So in other words, like, maybe I take a collection of fine-tuned models, just fine-tuned in the usual sense, and then just do PCA on that. Like, do I see this low-rank pattern? Like, is there any reason I should expect it? I don't think that's how this LoRa thing was derived originally. I think they just kind of guessed it and it worked okay. So we did that experiment and we saw it was a high rank space, which is surprising and weird. And it turns out that makes sense because the way that you initialize a neural network is Gaussian random, which is itself high rank. And so you wouldn't expect to see some low dimensional space of changes. So one kind of thing, a little gem that's hiding in the appendix of On's paper is a sort of proper notion of PCA you need in order to reveal that low rank structure, which really is there if you do that experiment properly. But anyway, I'll just refer you there if you want to read that, that kind of thing. So a little on time, we started late, so I don't actually know what time I'm supposed to go to.
When do we start? Like 10 more?
10 minutes, fabulous. Then I'll tell you about one more project we have related to the first one, which is all about kind of making interesting geometries for these learned latent spaces. I mean, one of the big problems we all face as academics right now is that our data, all these learned embeddings with these large models are fantastic and really interesting to study, for example, in the previous project, but we can't make them ourselves because they require so much resource and large data set. I think a reasonable question you can ask is, can we come up with training procedures that for smaller data sets maybe have similar patterns? And this project really was a byproduct of the first one. My student Chris worked on these closed form diffusion models and then asked, like, well, how could I make a really awesome learned latent space that bypass some of the really crazy training procedures that have been developed in the computer vision community? And that led our group, because we're full of mathematicians, to a very mathematically oriented project. So in particular, here's the problem that we studied in this particular project, which is this idea of something you call nuclear norm regularization. So the basic setup is as follows. I'm trying to learn some map, f of x, which maybe, for example, if you think about an autoencoder, it takes my data set and maps it to itself, after kind of removing noise, or it can map to a latent space. Either one of those is perfectly fine here. And there's a typical assumption, which we all talk about in machine learning, which sometimes people call this manifold hypothesis, which is the idea that your data set is curved, but kind of lives on some low dimensional object. For example, this letter S here is kind of intrinsically two-dimensional, even though it's sitting in three-dimensional space. And so a reasonable thing that you might want to do is to have a balance between two loss functions in this kind of problem. One is I want to just reconstruct my data set, right, if I'm trying to embed it. But the other is some regularizer that tries to encourage this structure. And specifically in mathematical terms, typically one way that this structure gets expressed is that the Jacobian of this map F, right, like my denoiser, for example, should be low rank, right? Because if a map has a low rank derivative matrix, that means it's kind of compressing things onto a lower dimensional space locally, right? And so the typical regularizer people use for problems like that is the nuclear norm of the Jacobian of your map. So the nuclear norm, in case you're unfamiliar, is the sum of the singular values. Right, so think about our like eigenvalues, pretty close. If you think about L1 norms, we'll work an analogy a little bit. Like I think one thing that's pretty commonly known is that L1 regularization makes things sparse under many assumptions and so on. So you can think of this as kind of like the L1 norm of the set of singular values, right? But in some sense, this is trying to make the sigma sparse, or in other words, it's pushing some sigma to be exact. So this is an object that, like for example, for an image denoiser makes a lot of sense, where maybe my F here is trying to take some noisy photograph and map it to like a cleaner one. And maybe you have the hypothesis that like the set of clean photographs is this nice manifold, the set of noisy photographs is like kind of a fuzzy thing around it, in which case some regularizer like this would make some sense. Here's the only problem is this is completely intractable the way that I've written that, right? So for example, here, if X is an image, so let's say that it has, I don't know, 10,000 pixels, right? Then JF is 10,000 squared pixels. Then I need 10,000 squared cubed operations or something like that to actually compute the singular values. And that's just to evaluate my loss function one time. So clearly back propagating through this thing is not feasible when X is high dimensional. And that's a real problem because it turns out it actually really is effective. So for example, here, we were able to train an image denoiser only on a data set of noisy images by adding this kind of regularization term. It's kind of fun, by the way, for diffusion models as well. Like, can I train a diffusion model that creates clean images if the only data set I have are noisy ones? The kind of questions that you can ask here. So in this project, what we asked is, can we make this tractable for machine learning? Like, this is clearly a useful thing in theory, but nuclear norm regularization is sort of out of the realm of things that one could do in practice when F is some giant neural network. And initially, this sounded totally wild to me, but Chris identified this interesting lemma, which is from the numerical linear algebra world, which is this little identity for the nuclear norm of a matrix. And essentially what it says is that remember that A star here is the sum of the singular values. This is a fun exercise to do in your scrap paper if you like fun calculus stuff. But essentially, one way to compute A star is that it is the minimum value where I look over all possible ways to factor my matrix into a product of U and V. These need to be full rank, by the way. This is not a low rank thing. Of the sum of the Frobenius norms of these two matrices. And in fact, actually, one of the early algorithms for doing nuclear norm regularized linear algebra really does use this kind of identity because Frobenius norm is easy to compute. The sum of squared elements. This is the thing that's tracking-ish. The other thing is we don't want a giant Jacobian matrix, but we'll come back to that later.
So yes. This goes further back than I thought, because I saw this in a paper of
Becca-Willett, maybe?
Recht and Fasel, right?
Yep, then Recht uses it. Becca-Willett has this formula is everywhere. It's like in the zeitgeist, kind of. We had a lot of trouble attributing it. I think this was the earliest one that we could find, but yes, this is earlier stuff out there. Yeah. So this is a fun lemma for computing nuclear norm. One might be tempted to do the following, which is to say, okay, well, maybe now I learn a field of U's and V's and somehow use that in my training procedure here. That doesn't turn out to quite work here because in order for that to work, you'd have to understand U and V as a function of X, which is kind of a complicated object. So instead, by some miracle, my student Chris was able to prove a really cool generalization of this fact, which takes it from linear algebra to nonlinear. So specifically, I'm afraid the setup of this is a little bit complicated, but bear with me. So if we go back here, let's think about what we're doing in some kind of functional language. If you think of A as a linear map, then I'm essentially decomposing A as the product of two linear maps here. So in analogy, Chris does the following. He says, okay, let's say that I have a map F from omega to its image, and I decompose that as the composition of two maps, H and G. Then essentially what he was able to prove is this kind of interesting result in variational calculus, which says the following. Here we have our nuclear norm regularized problem. This is the thing from the previous slide. If I, instead of optimizing for F, I optimize over a pair of functions H and G that compose to F, obviously I can kind of always do this. For example, I can make H identity in G, F, and then this is at least as expressive. If I regularize the Frobenius norms of the Jacobian matrices of those two pieces that get composed together, that is identical to regularizing the nuclear norm of F. This is just a nonlinear version of the theorem on the previous slide. And when I say just, of course, like 1,000 miles away, that's the case. Actually, proving this took him like about 7 or 8 pages of like annoying analysis. You have to be very careful because you need to understand how G and H depend on X, which is a little bit tricky. But I think from an intuitive perspective, it's not all that surprising. This is somehow just an extension of this fact to sort of a local neighborhood kind of situation. But what it allows us to do is to actually have a practical training procedure for nuclear norm regularized problems in machine learning. Because what are neural networks? Well, they're just a bunch of composed together stuff, all these different layers. So what do we do in practice? We just cut our network in half. We call the first one G and the second one H, or the other way around, I forget. And then apply that Frobenius regularization to those two halves of the neural network. And then what we find is the behavior of that is roughly almost exactly the same, by the way, as behavior of nuclear norm regularization of the whole thing. And that becomes more and more the case as your network gets deeper, right? Because that's what's justified by this theorem. And so this is a really interesting practical result. What it allows us to do is replace this giant SVD with a very simple Frobenius norm. Now, there is an implementation detail here, which is that differentiating your neural network is itself kind of an ugly thing. Luckily, we took care of that as well. But that's a more standard trick. So there's something called a Hutchinson estimator, which is a randomized estimator of the Frobenius norm of the Jacobian of a matrix, of a function rather, which is very simple. You just take your function and you evaluate it at a randomly perturbed location. It's kind of like a divided difference. And as long as this guy is Gaussian, you can show that this converges to the norm on the left-hand side. So at this point, if you take all those pieces and you put them together, you have an extremely efficient technique for nuclear norm regularized problems in machine learning. So rather than computing a giant SVD, we now just evaluate our network twice. And it turns out that those things are equivalent. So we can validate that on a lot of classical problems. There's a famous model in image processing, which happens to take this form, and indeed it converges to the right thing. We also applied it to some problems with denoising, and then to bring it back to that first project, we used it to create useful autoencoder style architectures that make nice embeddings for our data set, and then use that to sample in the closed form diffusion paper to pretty good result. So in any event, I think I'm out of time. So hopefully you get the idea that essentially, even in this new world where we're all operating with these large models that none of us can actually optimize, there's still a lot of really cool and interesting both kind of optimization and statistical oriented research that we can do with a geometry flavor that's leveraging the interesting shapes that are learned by these models, even if it's a little bit intractable to train them from scratch. I attempted to come up with a schematic that kind of shows how these papers link together. You know, some of them are dealing with the nose and the edges of this graph, but I don't think this matters a whole lot. I think the main takeaway here is that there are some really interesting things to be done by just peering into the architectures, editing them in different fashions, coming up with small interventions, and really understanding exactly the effect of the training procedure, the data set, and the architecture on how these different inferences work. So in any event, it is my pleasure to grab coffee with anybody this afternoon. I really want to learn about all of you guys' work. I'm so grateful for the invitation here, and thank you so much for taking the time.
So in the interest of time, if you do have questions, feel free to come directly here. Let's get the speaker again.